Hello guys, nice to see you. Okay. During last lecture, we kind of finished discussion of pure electrostatics. And now we proceed further along our course. And today's topic, which we will start, is capacitors and capacitance. So this is a feature of conductors, some of random average, like arbitrary shape, to accumulate, or systems of conductors, which is called actually capacitors, to accumulate electric charges. And experimentally, has been shown that there is certain linear dependence between the electric charge which is accumulated by a conductor or a capacitor, a system of two conductors, and difference in potential between these two conductors in the capacitor, or just potential of the body if we consider accumulation of electric charge on some isolated conductor. So let me change the camera and let's go into this topic. So let us consider two conductors of arbitrary shape. One is positively charged, plus Q, another negatively charged, minus Q. These charges are equal to each other by absolute value, but different inside. So there will be some electric field between these two bodies. So some electric field lines which originate on positively charged conductor and terminate on negatively charged conductor. And such a system of two conductors is called capacitor. And in electrical circuits, you see that quite often it's shown like this, two parallel plates with some wires coming to it. So it's shown like this because of one of the most common type of capacitors are parallel plate capacitors. So when there are two parallel plates and they form a system of two conductors, which is called parallel plate capacitor. Also, you may see some signs like this with an arrow, and that means a tunable capacitor. When you can change the capacitance of this capacitor, and that could be useful either to tune some electric circuits or to tune some resonant LC circuits, and go in resonance with some external electromagnetic signals. So we will talk about this in the future, but these are two most common ways how capacitors are shown on electric circuits. And the question is how we, what will define the properties of such a system of two conductors of this capacitor to accumulate electric charge. And experimental, like empirical data show that there is some linear dependence between accumulated electric charge. So it's linearly proportional to the difference in like potential difference between these two bodies. Let's say we have potential 1, potential 2. So the absolute, this delta V is the absolute value of the difference in between potentials V2 and V1. So here we care only about absolute difference because it doesn't mean if it's like increasing potential, decreasing potential. We care about difference in potential, its absolute value. And there is, since it's linear dependence, we definitely have some coefficient which defines this dependence. And for different systems of conductors, for different capacitors, this coefficient obviously will be different. So in general, you can write that electric charge is equal to some linear coefficient C times delta V. And this coefficient C is actually the capacitance, the feature, the property of the capacitor to accumulate its ability to accumulate charge, and it's defined as accumulated charge divided by potential difference between the plates. So these conductors, doesn't matter what shape they have, they are called as plates of the capacitor. And capacitance is measured in, so from this equation, we already see that it's Coulomb divided by voltage. And in order to deal with capacitance, was proposed a special unit, which is farad. So to describe it, the meaning of 1 farad, so a capacitor possesses capacitance of 1 farad if by accumulating of 1 Coulomb on its plates, the difference, potential difference between plates increases by 1 volt. So it's necessary to mention that farad is a very big quantity, 1 farad. And usually people operate with picofarads, nanofarads, and microfarads. So that's 10 to minus 6, 10 to minus 9, and 10 to minus 12 farad, respectively. So obviously this is quite big quantity, and usually all capacitors are much smaller. They possess much smaller capacitors. So let us consider what happens when we attach a capacitor, like system of 2 parallel plates, or whatever, any system of 2 conductors, to some power source. We have some DC power source, direct current power source, so just constant polarity. And we contact with different terminals, different plates of this capacitor. So once we attach these plates to terminals of the power supply, we change the potential of these plates. Initially, they were not charged, their potentials were the same. But now we create some potential difference, which will be dV, and it's defined by the voltage difference between potential difference between the terminals of this power supply. So once we have some negative potential attached to the left side of this left plate of the capacitor, we kind of move electrons in this plate. So we kind of have excessive electrons in the plate. And since we have this, they don't come from nowhere. Obviously, we need to extract them from somewhere to accumulate in the other side. So they are extracted from the positively charged plate, and behind them, positively charged ions in crystalline lattice, which the plate consists of this conductor material. They remain because electrons are moved. So electrons are moved and accumulated to the left plate of the capacitor, and remaining positively charged ions in the crystalline lattice create some, build up some positive electric charge at the right plate of this capacitor. So this rearrangement of electrons will continue until the moment when the internal electric field between these two plates. So the more electrons we rearrange, the more we accumulate at the left side of the capacitor, and less of them remain on the right side of the capacitor. This electric field in between two plates will increase, and this will continue until the product of this uniform electric field. So we assume that it's quite large plates, and we have uniform electric field between the plates times thickness, like of this capacitor, distance between two plates, will not be equal to delta V. So this is the difference in potential difference between the terminals of the power supply. And then we will get some equilibrium. So then this rearrangement of electrons will stop, and we will have a steady state when one plate is charged negatively, another plate is charged positively. So now this is like general explanation of the capacitance, like physical meaning of capacitance, and some basic electronic processes which happen during the process of charging a capacitor. And from this qualitative description, it's time to proceed further for some quantitative analysis of capacitance and calculation of capacitance. So first of all, let us consider just single conductor, like spherical conductor with some radius. Let's call this radius A. And let's assume that this sphere, conducting sphere, is charged with, let's say it has some positive charge on its surface. And its potential, its surface potential is V1. Then in order to calculate the capacitance of such a conductor, so we need to imagine some shell which surrounds this sphere, and the radius of this shell, r capital, approaches to infinity. So it's huge and located like very far away from the surface of this central sphere, electrically charged. And of course, we can assume that this infinitely large conducting shell possess some negative charge Q, and its potential V2, since it is it possesses such large radius, will be set to 0. So we know that potential of a sphere, electrically charged sphere, will be equal to Coulomb constant times electric charge accumulated on its surface and divided by radius. So this will be V1, this potential of the surface of the small sphere. And V2, respectively, will be Ke times Q, it accumulates the same charge, divided by R capital. And since R capital approaches to infinity, it's in denominator, and we have the case when V2 also approaches to 0. So that's why the voltage potential difference between this infinitely large shell and surface of the sphere will be just V1, the potential of the sphere. And now we can calculate the capacitance of this sphere. So we know that capacitance is equal to electric charge accumulated divided by potential difference. And in this case, we have electric charge Q, and what is potential difference? Potential difference is V1, and V1, like its surface potential, is given by this equation. So we put here Ke times Q and divided by A, which goes in the numerator. So Q and Q cancel out. We get A divided by Ke. And considering that Ke is equal to 1 over 4 pi epsilon 0, we get final expression. It will be 4 pi epsilon 0 times A. This is equation of the capacitance of a sphere, conducting sphere. And you see that here we have, this is a constant, like 4 pi and epsilon 0, this is permittivity of free space. And the only parameter which defines capacitance of this sphere is its radius, means that only the geometrical factor determines capacitance of this sphere. This is very important because we don't see any dependence on amount of electric charge it accumulated or surface potential of this sphere. So these parameters do not influence on the capabilities of this sphere to accumulate charge. And that is defined only by its geometry. In this particular case, capacitance of a sphere is equal to 4 pi times epsilon 0 times radius. So now let's go to a capacitor. So a system of two conductors, and of course, the most common is parallel plate capacitor. So we have two plates, parallel plates. One of them is charged positively, one negatively. And there is, so we consider these plates to be large, like much larger than the distance between the plates. Let's call it D. I mean, the linear dimensions of these plates should be much larger than the thickness of this capacitor. And we have, in that case, some uniform electric field inside this capacitor. So this electric field for a system of two large plates, which with linear dimensions much larger than the distance between plates, is equal to sigma surface electric charge concentration, surface density of electric charge divided by epsilon 0, assuming that we have vacuum in between these two plates. So this in other form can be expressed as total electric charge accumulated by the capacitor divided by epsilon 0 divided by the area of the capacitor. So in this case, what will be the potential difference between these two plates? So delta V. It's quite easy to answer this question because the electric field is uniform and we have distance between plates. That's why potential difference will be the product of uniform electric field and distance between plates. We can now write that it will be Q times D divided by epsilon 0 times A. Good. Then we know charge, we know potential difference. We can calculate capacitance of such a capacitor, parallel plate capacitor. It will be Q over potential difference. And here we have Q over Q D times epsilon 0 A. So we cancel out this Q and get the expression for the parallel plate capacitor, where we see again there is no dependence on electric charge or like difference of electric a potential difference between plates. There is only geometric factor. There is area of these plates and distance between plates. The same as with the first example, only geometrical factors of the isolated conductor or a system of two conductors, which is called capacitor. Their capacitance ability to accumulate electric charge depends specifically on their geometry and is not defined by accumulated electric charge. So going further, we need to consider some like more advanced systems, capacitors, next example will be a cylindrical capacitor. So we have some conductive rod, and around it we have a cylinder, conductive cylinder. So this. So let's also so here is the length of this cylinder. Call it L. Maybe it's better to draw from like the cross section. So this is the cylinder. This is the conductive rod inside this cylinder. This radius A of the conductive rod, radius B of the cylinder, and let's assume that we have positive charge on this conductive rod and negative charge at the cylinder. So in this case, we have some symmetric, like cylindrically symmetric electric field, because we assume that the difference between radius is much smaller than the length of the cylinder. And in this case, we have symmetric, the electric field inside such a capacitor possess some cylindric symmetry. And in this case, we need to, let's define what will be electric field. I don't recall that we calculated electric field inside a such system of two conductors. So let's maybe do it now. Let's define what will be the electric field inside this capacitor. For that purpose, let us choose some Gaussian surface, like closed surface. It will be cylinder with the radius R. And let's find the flux of electric field flux through this Gaussian surface. Since we have a cylindric symmetry, flux through the edge sides of this cylinder will be equal to 0, and total flux will be defined only by flux of electric field through the side surface of this Gaussian cylinder. And in this case, we can write that the electric field flux will be equal to electric field times side surface of this cylinder. So it will be 2 pi r, length of this circle, times L, the height of the cylinder. And we also know from Gauss' law that total electric field flux is equal to the electric charge enclosed in this Gauss surface divided by epsilon 0. And this electric charge, so what is charged inside this cylindric closed surface? We have this central rod. And for this central rod, we have some uniform linear distribution of electric charge along this rod. So it will be like this linear density of this electric charge is lambda times L, like times the length of the rod, which is the length of the cylinder, divided by epsilon 0. So from here, we can express the electric field, and it will be lambda divided by 2 pi epsilon 0 r. We have some cylindric symmetry. It reduces, this electric field reduces reversely to the radius, the distance from the central axis of the rod. And in terms of the Coulomb constant, we can write that it's equal to 2 times k e lambda divided by r. Good, so we have electric field, and now we need to calculate the potential difference between the central rod and this cylindrical surface around it. So for this purpose, we recall that, so let's call V B and minus VA. So we have here surface of this rod is at potential VA, and here surface of this cylinder at potential VB. So the difference, potential difference, will be equal to minus integral from A to B E R dr, assuming the cylindric symmetry. So in this case, we substitute now electric field of inside this capacitor, and it will be 2, so minus 2 ke lambda integral dr over r from A to B. So this will be equal to minus 2 ke lambda integral from A. Oh, sorry, we already integrate already here. So the integral of this dr over r, it will be natural logarithm of r from A to B. So continue further, we need to take this to get the final expression will be minus 2 ke times lambda will be natural logarithm B minus natural logarithm A. And taking into account the properties of logarithms, difference of logarithms is equal to the logarithm of the ratio. So we can write minus 2 ke times lambda times natural logarithm of B divided by A. So this is our expression, and now we will write it down on the next slide and proceed further with the calculation of the capacitance of such system. So VB minus VA will be equal minus 2 ke lambda times, what, I missed something? No, times natural logarithm A divided by, not B divided by B divided by A. So now we calculate the capacitance. So capacitance is equal to electric charge divided by potential difference. And that is electric charge divided by absolute value of this potential difference VB minus VA. Now we can substitute, instead of electric charge, accumulated charge, it will be lambda times L, linear density times of electric charge distribution times length of the cylindrical capacitor. And instead of this, we put final expression. It will be, but it's an absolute value. And we don't put this minus here. It will be 2 ke lambda natural logarithm b divided by a. So here we again cancel out this lambda linear distribution of electric charge, linear density, and with the expression for the capacitance of cylindrical capacitor, 2 ke natural logarithm b divided by a. Again, you see that in this equation, there is no electric charge accumulated, there is no potential, there is only geometric features of which describe the symmetry and the size of this structure of this capacitor. Another capacitor which we need to consider is a spherical capacitor. When we have, like in cross section, like two spheres, and one has radius A, another has radius B. So in this case, we know that electric field inside such system will be Ke times Q divided by R squared. So it's distance from the surface of the charged sphere. And again, following the same procedure, we consider potential difference between the internal sphere and potential difference between the external sphere. So VB minus VA will be equal to minus integral from A to B ER dr. So here we have spherical symmetry, and this will be equal to minus KE Q integral from A to B dr divided by R squared. So we get the result. It will be minus KE Q 1 over R from A to B. And final result will be KE Q 1 over B minus 1 over A. If we set to the common denominator, KE Q A minus B divided by A times B. Yeah, I forgot this minus in front. Okay, once we have the potential difference between these two surfaces, we can calculate also the capacitance. So capacitance will be Q divided by delta V, and this is Q divided by Q let's check here. KE B minus A, and here will be A B. So we cancel out these electric charges and have the expression for the capacitance of the spherical capacitor will be radius of internal sphere times radius of the external times Coulomb constant and difference between these radiuses. So what is interesting if we consider this equation, which also defines only the geometric features of the capacitor, we consider some limit of B radius of the external sphere approaching infinity, then this equation can be represented. So we can neglect with A in the denominator because B is very large, and then it will be A times B, KE times B. So B and B cancel out, will be A divided by KE. And this is capacitance of this spherical conductor, which we derived at the beginning. So we see that in this particular limit, when external sphere is approaching, like its radius approaching infinity, we end up with capacitance of just a single sphere. Now we need to consider how capacitors can be connected, and we will just describe today. Yeah, let's try to do it. It's not so much of information. There are two ways of connecting capacitors. They can be connected either in parallel or in series. So let us consider today parallel connection of capacitors, and already next time we will deal with the series connection. So parallel connection, let's say we have two capacitors connected in parallel, and there is some power supply. Plus, plus, minus, minus. At parallel connection, doesn't matter what we connect. In this particular case, it is capacitors. Their terminals are connected to the same terminals of the power supply, means that there is no voltage drop between each of these terminals, and that's why voltage, like this potential difference between terminals of the power supply and between this contacts to capacitors will be the same. So we put like delta V1, so it will be capacitor C1 with capacitance C1, it accumulates charge Q1. This is C2 accumulates charge Q2. And the voltage, like potential difference between its plates is delta V1, and for the second one, delta V2. So in the parallel connection of these capacitors, we can write that delta V is equal to delta V1 and is equal to delta V2. So potential difference between both plates of both capacitors is the same. Now let us consider what will be total charge, which is accumulated by these two capacitors. So total charge is equal to the sum of two charges accumulated at capacitor 1 and capacitor 2. So it is possible to replace these two capacitors with one capacitor with some equivalent capacitance. So that will look like this. We have just one capacitor, also the same power supply, minus delta V. And here it will be C equivalent and will accumulate Q total. So our task is to calculate what will be this equivalent capacitance of two capacitors connected in parallel. We know that total charge relates to the potential difference at the plates via the equivalent capacitance. So it will equivalent capacitance times delta V. And we know that total charge is the sum of charges accumulated at each of the capacitors. So that's why we can write that C equivalent times delta V is equal to C1 times delta V plus C2 times delta V. So here we can cancel out all these differences, potential differences, because they are the same. And as a result, we get the expression. Equivalent capacitance of two capacitors connected in parallel will be equal to the sum of their capacitance. So this is 2. So in general case, we need to write when we have like n capacitors connected in parallel, we should write that C equivalent is equal to the sum over I, like from I equal to unity to I equal to n of Ci, like we just sum up capacitance of each capacitor connected in parallel. So this is quite straightforward and simple rule, which you definitely need to remember because there will be many problems involving this calculating equivalent capacitance of different batteries like of capacitors. So next time we will consider the series connection of capacitors and proceed further with the accumulation, like the energy accumulated inside these capacitors. Since it accumulates electric charges, concentrates some electric field inside, and this electric field possesses some energy, which we will learn how to calculate. So summarizing our today's lecture. So we introduced the concept of capacitance, considered like units, and described the most like general concept of accumulation of electric charges on conductors, calculated capacitance of isolated conductor, and also system of two conductors, like different systems of two conductors, which are called capacitors. So it's parallel plate capacitor, cylindrical capacitor, and spherical capacitor. And also considered how to calculate equivalent capacitance of capacitors connected in parallel. Okay, thank you very much for attention. If you have any questions, you're welcome.
Sorry, Professor, which chapters from the book we need to go through for preparing to our midterm exam?
So midterm will be on next Saturday, and we will include in the midterm material which actually we considered today, capacitors, but up to today. So topics which are going to be considered already on next week, like Monday, Wednesday, and Friday, they will not be included in this first midterm. They will be included like later for the second midterm.
Okay, thanks.
You're welcome. Good, guys. So keep in mind, please don't forget that this midterm is coming, so it will be Saturday quite soon. Revisit all topics we discussed on our lectures, and also what is according to the subject manual recommended from the textbook. And yeah, be prepared for the midterm on next Saturday. But definitely I will mention you on the way when we are approaching this date. Good, thank you very much for attention, and have a good evening and good weekend. Take care.